So now that we've played around with these a little bit, here's a definition for a limit of a sequence. Now, this is not a super formal definition. Students often struggle with the technical definition for the limit of a sequence, so this is a little bit more user friendly. We're going to say let, and again, we have our sequence being a set of numbers, so it's inside set brackets. Let a sub k be a sequence and L a real number. If a sub k approaches L to within any desired tolerance as k increases without bound, then the sequence converges to L. So that's when we say that the sequence converges, and we say that the limit as k approaches infinity of a sub k is L. Otherwise, the sequence diverges. And as we saw in our previous examples, it may diverge to infinity, negative infinity, or neither of these, which was the does not exist case. We're going to once again kind of do a modified version of the textbook examples. I've modified the directions here, and these are going to be the directions I'd like you to use on the homework assignment as well. For the sequence with the general term given, write out the first 5 terms, view the graph, and then state the limit of the sequence if it exists and whether it converges or diverges. So we'll begin by listing the first 5 terms. I'm going to begin with k equals 0 for the first example because I know sine of 0 isn't undefined. It will have a value. So my sequence, a sub k, will be the set of numbers starting with sine of 0, going to sine of 1, and so forth. In calculus, we always use radian measures, so these are angles of 0 radians, 1 radian, 2 radians, 3 radians, and so forth. We can pick up a calculator to get the decimal approximations for each of these. I went ahead and rounded each decimal value to 3 decimal places. You need enough decimal places so that you're sure you're seeing the trend of what's happening, even if the change might be very small. And here's the first caution. You've got to make sure that when you're looking to determine the limit of a sequence, that you look at a sufficient number of terms. For instance, if you were to only look at the first 3 terms, you might think that sine is just getting bigger and bigger without bound. But you're familiar with the graph of sine, and so you know that it has a periodic behavior to it. You can opt to look at the graph of the function, although you need to keep in mind again that technically the sequence is not continuous. It consists of discrete values. Or if you're using a program like Desmos, you can have it just graph the individual points. I have Desmos graphing the first 9 terms. And again, what you can see is the initial part of sine goes up and almost seems like it could be approaching 1. But then it takes a turn and heads towards negative 1. Then it takes a turn and heads towards positive 1. So what would we say about the limit? Well, it's not getting closer and closer to any particular value. It keeps heading to some extremes of either positive 1 or negative 1. So now that we've looked at the graph, we've confirmed what we really should already know, which is that the limit as k approaches infinity for sine of k is going to be a situation where it just does not exist. And because it does not exist, we say that the sequence diverges. It's not heading towards any particular y value. In the next example, we have a sub k equaling 2 to the k power over, and my apologies, this should be k squared. So I'm going to write out the first few terms. And because I have a k squared on the bottom, again, I don't want k to be 0, so I'm going to start at 1 with the term 2 to the first power over 1 squared. Then we would have 2 to the second power over 2 squared, and so forth. So I've written out the first 5 terms and come up with their decimal equivalents. And at this point, it's a little bit hard to see what this sequence is doing. A graph allows us to see more values. So let's go look at the graph. First, here's the graph of the function. And again, we would ignore the part that's below 0, and we would not include 0 either because we know there's a discontinuity there. So we're looking at the sequence created by the integer function values starting at 1. So again, if you like, you can have Desmos turn on those particular points. And you can see there is an initial downward trend, but then the values continue to trend upwards. And because I've graphed the function, I can zoom out and see, yeah, they're just continuing to head towards infinity. So the limit of this sequence is infinity, which means it diverges. So if the limit is infinity, this sequence diverges. And in the last example here, we have our sequence as k to the 1 over k power. Begin by writing out the first couple of terms, first 5 terms. Notice again, I've opted to start with k being 1 because 0 would make an undefined fraction. And the starting place of a sequence really is kind of irrelevant because what you're focusing on is the trend, where the terms of the sequence are heading. So you care more about the tail end behavior of the graph than you do the start. I would once again get some decimal equivalents to see if I can detect a pattern there. And from the decimal approximations, it seems like we have a little bit of an oscillating behavior going on where the function goes up for a bit, then back down. So again, what a graph is going to let us do is to see many more terms in the sequence. So we'll go there next. And I can zoom out, and it does sort of seem like it's settling towards a value, like there may be some convergence here. Again, you can switch from the continuous function to the sequence, you can switch to see the pattern in the points. So it does seem like it's trending somewhere. If I go back to the function, I can actually trace along here. So see how I'm a value slightly above 1. I can zoom out, zoom out, zoom out, and then check again. Yeah, we're getting closer to 1 in the y values. I can zoom out some more, still getting closer to 1. So it seems like this sequence is going to converge to 1. So the limit as k approaches infinity of k to the 1 over k power will be 1, which means that this sequence converges. For your lab this week, I'm going to have you looking at sequences. And because you'll be using Mathematica, you can look at as many terms as you want. It can calculate the first 5 for you, the first 100, the first 1,000, which gives you a much better chance of spotting the pattern that's happening. Although again, the visual information given by a graph is really useful as well.